Hello. In our last lecture, we started talking about phase modulated sensors, and we essentially said whenever you want to measure phase, your optical receiver is not sensitive to phase changes. So you'll have to use sort of a demodulation mechanism where any phase changes can be converted to intensity changes or amplitude changes, which can further be picked up by the optical receiver. And with respect to that, we said we need to, phase is not, especially when it's propagating over long distance, is not something that you can measure in absolute terms. So you need a reference, and so typically you use a reference which is protected from whatever perturbation you are trying to measure, and then you will be able to pick up any phase change between the perturbed radiation and the unperturbed reference, right? And in this respect, we said a common sort of apparatus that you use for picking up these phase changes is an interferometer, right? So we're going to move on today to go a little deeper into this. So we went on to understand interference, the interference phenomena, and we went on to look at the output of an interferometer with respect to phase changes. We looked at what is the optimum point for operation, and then went on to look at one realization, one example of an interferometer, or maybe a relatively simple example of an interferometer is the Michelson interferometer, where the optical source is split into two parts by this 50-50 beam splitter, and both those parts are reflected back, so they essentially the beams folded back, and then it comes to the optical receiver, where when both these beams are coming together, they are incident on the photodiode. The photodiode essentially looks at the beating of those two fields, and the corresponding intensity that we get, we derived it as something like this. So essentially, if we were to look at this, delta phi now with respect to this apparatus, we say delta phi is equal to 2 pi over lambda n1 d1 minus n2 d2, right? And where d1 and d2 are essentially the round trip path length in this setup, right? And then we also made this point that this sort of an interferometer is going to be very, very sensitive to path length changes. So we said even if the path length changes are in the order of lambda by 2, right, you're going to be having a large change. Essentially, you will go from maximum to minimum or minimum to maximum whenever the path length changes by lambda by 2. And the fact that in our case lambda is in the order of 1 micron, maybe 1.5 micron, whatever wavelength you choose, it's around that order. The fact that we have this thing in order of wavelength in the order of 1 micron means that delta D is in the order of half a micron, and that's to go from maximum to minimum. So if you want to actually measure small phase changes, let's say in the order of a fraction of pi radians, then that can easily get immersed even if its perturbations the order of 100 nanometers. And that I am talking about only in terms of physical path length changes, but that could also happen because of changes in the refractive index N1 and N2. Of course, we are showing this as a medium where it's all free space. So you may say the refractive index doesn't vary much, but that's again a relative quantity. Even if you are having some pressure changes because somebody is opening the door of the room where this interferometer is set up, that actually changes some pressure, and even if the changes in pressure causes changes in refractive index in the order of 10 power minus 6, right? Refractive index changes of 10 power minus 6 is enough to destabilize the interferometer, move it from maximum to minimum and so on. So it's a highly sensitive apparatus. So you need to somehow rein in all of these effects and use it to measure only the perturbation that you are interested in, and that's actually a huge challenge. That's one of the biggest challenges as far as using these interferometers are concerned. Okay. One possible way of doing that is by going through an all fiber setup instead of this setup where it's all alignment sensitive. You need to put the beam split in the right place, you need to put the mirror in the right place, and then fold it back, make sure you're getting collinear beams all across, and so the interference in this arm, the beams are collinear, and then you need to maintain it that way, and that means that the relative position of all these, especially the two mirrors and this beam splitter, has to be quite sturdy. Like we said, even in the order of fraction of a micron can destabilize the entire setup. So that actually puts a lot of constraint on the setup, and to the point that if you were to do a practical sensor, on-field sensor, it's going to be extremely challenging to do that in a reliable manner. So that could potentially be addressed by going to an all fiber interferometer. Okay, so that's what we'll go to check next. So we're generally talking about challenges in phase measurements, and one of the first challenges we're talking about is stability of interferometer. So you may want to say that, okay, instead of using a free space setup like what we were seeing before, you could potentially use an all fiber setup. So what does an all fiber setup look like? You have once again this optical source, okay, and then the optical source, let's say it's a fiber pigtailed semiconductor laser or an LED. Right, so you have a fiber optic device which is called a power splitter, a coupler basically, and what we are going to use is a 50-50 coupler, which means that 50% of the light that's coming through this incident in that coupler will go in this direction, and the other 50% will go in the other direction. right? So, well, how does it work? We're not going to spend much time on it right now, but I can tell you quickly that essentially you have the two core, the cores corresponding to two fibers. They are brought very close to each other such that the evanescent field of one waveguide is actually overlapping with the evanescent field of the other waveguide, and so you are essentially able to leak light from one waveguide to another waveguide and back, of course. But if you get your interaction length right, you can achieve the kind of split ratio that you are interested in, right? So so those are available, commonly available in fiber form, what is called a fused biconical taper sort of coupler, right? So so let's say we have one of these couplers and we can split it into two. So why two? Well, now you can use one arm as your reference arm and other arm as your sample arm. Okay, so for example, you can take this arm and you say, okay, I'm going to put a lens over here, right, which will essentially collimate the light that's coming over here, and then I will put my mirror over here so that I can fold the light back. And on this side, I'm going to put another lens. So once again, I can collimate the light, and then I will put my whatever sample that I'm interested in measuring, right? So this sample could be, let's say, a wafer. In semiconductor processing, you want to understand what is the roughness of a wafer. You want to check the roughness of a wafer. And if the roughness measurement has to be made with let's say tens or hundreds of nanometer accuracy, right? You can put that into through one of these interferometers, and all you do is you basically translate the sample across. So you can move the sample across, and then you can actually map out the surface roughness of this sample, right? So that could be a potential application. Now, like we talked about, this is going to be your reference, and clearly in this sort of arrangement also, your reference has to be absolute, meaning that there should not be any phase changes within that reference. So you need to make sure that this particular portion here, right, it's actually well protected, and so it's not susceptible to external perturbations, right? Because unless you have a very stable reference, you're not going to be able to make very precise measurements of changes in phase. And of course, you'd argue that, why can't I coat the end of the fiber itself with dielectric coating, so it essentially acts like a mirror. And those are once again things that people have looked at before, so they could potentially coat the end of the fiber itself, and that would be quite a rugged setup if you do that. But of course, if you have an external mirror, it gives you that opportunity to potentially move that mirror, right? Slightly dither that mirror, so that you can look at a corresponding change in the along the depth of the sample. Okay, we'll come back to that in a minute, but that could be one reason why you may want to actually have an external mirror instead of putting a mirror coating at the end of the fiber. But essentially, you do all your detection using an optical receiver, okay, and Yeah, that sounds like a relatively simple arrangement. Yes, you do have a free space part over here. So there may be some alignment issues. Like I said, here this can be put in a small capsule, so it's actually occupying much less space, and overall you've taken out all the complexities of the alignment, and you have brought it down to only these regions which are relatively small. So it's a much better arrangement. So you could actually have a much more stable setup for doing this sort of measurements. And of course, what we looked at before actually holds good here as well. So you could basically use the same sort of analysis and say the total intensity here corresponds to the beating of the fields from these two arms, and then any relative phase changes between those two arms, like we talked about. This phase change corresponds to 2 pi over lambda multiplied by n1 d1 minus n2 d2. That could be actually any changes in that could actually be measured very accurately. And of course, we are interested in measuring changes in D2. Let's say this is D1 now, and this is D2. Those are the round trip path lengths in the respective arms. We are looking at changes in D2 with respect to D1, but you have to be in an all fiber configuration. You have to be very wary about this quantity also, this refractive index of the optical fiber. Why? I already mentioned that over here also, even if there are some pressure changes in the two arms, that changes the refractive index, and that could potentially cause perturbations, unwanted, undesirable perturbations in your measurement, and more so over here because the optical fiber, which is made of glass, that glass is actually susceptible to changes in the environment. Essentially, if there are changes in let's say strain or temperature of the environment, that can actually change the refractive index. The dn over dt, the what we call the thermo-optic coefficient, is in the order of 10 power minus 6 for glass, and similar order for dn over d epsilon, which is essentially what is called the strain optic coefficient. So small changes in those quantities can actually perturb this thing. So you still have that issue, but let's just say for a minute that we have some way of dealing with that. We'll come back and see what is that way, but let's just go with that. Okay. Now clearly this sort of setup is much more easy, much more rugged, and so much more easy to package into an instrument. So that you put the entire thing into a compact box, and you just have well, this one, the reference is still within the box, but this particular point where the fiber probe is coming out with a lens, and that's, you just have a collimated beam available. That's the only part that of this optical setup that comes out, and then that actually probes the external environment. In this case, like we talked about, it could be a silicon wafer that you are trying to find the reference of. Okay, all good here. I do want to make a point about the optical source at this point, right? So let's just see what sort of optical source would you use. We made this argument that we have been all along, we've been talking about phase with respect to we quantified phase as 2 pi over lambda multiplied by n multiplied by L, and then we drew this waveform and all that to represent the wave. But when we draw a waveform like this, what we are essentially saying is it has a very specific frequency, and then it corresponds to a very specific lambda. And so essentially what we are alluding in all this discussion, it's a monochromatic source, right? So does it have to be a monochromatic source? Does it always have to be a monochromatic source? Well, there's of course there's no such thing absolutely as a monochromatic source. You are essentially talking about highly temporally coherent sources which are essentially having very narrow line with maybe the order of kilohertz, right? Do you really need that sort of order so that you can actually have this interference happen, or can you tolerate with broader light sources like a fabric or a laser, for example, has got it's not kilohertz, it's in the order of gigahertz, or maybe hundreds of gigahertz. Can you still get reasonable interference with that sort of a source? So that is our next challenge, right? So let's actually examine that a little more closely. What is the role of source coherence in all these phase measurements? Okay. So the second thing that we want to investigate is role of source coherence. So of course, when we talk about coherence, we can actually characterize it as either temporal coherence or spatial coherence. Okay. So spatial coherence, as you know, is how well two points across a wavefront are correlated. And if you are talking about light actually coupled through, let's say all of these fibers, sorry. So all of these fiber is single mode fiber, right? So it's only one mode in that, and then the fundamental mode in an optical fiber, as you probably know, is it's close to a plane wave essentially, right? So it's a highly spatially coherent, right? It's one of the best spatially coherent sources that you can get. So that is not an issue, right? So this one, you say, we have taken care of it just by going to an optical fiber based setup. So the question really is, what about temporal coherence? What is the role of temporal coherence in our interference? Now let's just go back and look at this picture here. We said the total intensity of this interferometer corresponds to beating of these two waves, E1 whose fields correspond to E1 and E2. And when we talk about beating of the two waves, you are essentially looking at the what is called the this beating corresponds to what is called the mutual coherence function, right? So this is G12, and similarly this can be called as G21, or you can just call it G12 conjugate. So this is actually what is called the mutual coherence function. Okay, and so that is actually a quantity with units in the order of intensity, but but if you want to really look at the degree of coherence, so you say, okay, on a scale of 0 to 1, 0 being incoherent and 1 being absolutely coherent, you want to you essentially want to characterize the coherence of the source. You could use what is called a degree of coherence. So instead of the mutual coherence function, you can actually define a quantity called degree of coherence G12 such that it's this capital G12 divided by the basically the total intensity corresponding to the two waves, right. So because E1 multiplied by E2 is going to give you an intensity. So if you divide that by the intensity, so you are normalizing the mutual coherence function by the intensity, then you can actually get a fractional value, a value between 0 and 1. Okay. So essentially what we are saying, coming back to this, when you are looking at when you want to actually account for the role of coherence, you need to now write this expression. The total intensity of the interferometer is going to be given by I1 plus I2 plus G12 plus G12 conjugate, right, where G12 corresponds to the mutual coherence function. Okay. So in the previous case, we assume that it's absolutely perfectly coherent source. So we did not worry about writing out G12, that is the small G12 separately, because small G12 was equal to 1. Right, but now we want to actually understand the effect of coherence. Okay, so we will just write it out explicitly like this, and G12 is actually a complex value. So you know that the addition of a complex number with its conjugate is going to give you 2 times the real part. So you will get I1 plus I2 plus 2 times the real part of G12, right. And of course you can write this as I1 plus I2, and you bring out, you write G12 in terms of root of I1 I2 multiplied by small G12, which is the degree of coherence. So you can say this is going to correspond to root of I1 I2 multiplied by 2, and real part of this degree of coherence, which we said is G12 is a value between 0 and 1, 1 being perfect coherence and 0 corresponding to incoherent, or you can call it perfectly incoherent light, right. So in this, and G12, mind you, has got an amplitude, a magnitude as well as phase. In fact, what we are talking about here is actually the magnitude of G12 is a value that's between 0 and 1. So if you want to write it out clearly, you will say that I1 plus I2 plus 2 root I1 I2, and then you write this as magnitude of G12, and then the phase term, and the phase term is once again just that complex e power j phi j delta phi term, and so real part of that is going to give you once again cos of so cos of delta phi. Okay, and if I1 equal to I2 equal to I naught, as we have, if both the intensities are equal, so you can just write this as 2 times I naught 1 plus G12 cos of delta phi. Okay, so essentially what is different about this, this is our total intensity now, is the fact that we got this additional term here, this magnitude of G12, which is actually corresponding to the degree of coherence, right, of our source. Okay, so let us actually see what is the effect of that. So previously we were assuming that this G12, magnitude of G12 equal to 1, and that is what gave us this sort of thing. If it is if G12 is absolutely incoherent, if G12 is equal to 0, then this B term goes out, and then you just have a flat line at 2 times I naught, and that does not really help anyone, right. If then if it is absolutely incoherent, then you are not going to be able to use this as a phase modulated sensor. Okay. So there is a certain need for coherence, and in this case what we are talking about is we are not talking about spatial coherence, because that is already taken care of by the optical fiber. We are talking about temporal coherence. So now we are saying we need a temporally coherent source so that you can get an interference. Now if you want to really look at what is the effect of that, then we say for G12, which is actually magnitude of G12 which is between 0 and 1, let us say around 0.5, then you are looking at a waveform or a dependence that's like this. So it is not going to the high of the highs, the absolute maximum or absolute minimum, it is somewhere in between, and this visibility of these fringes with respect to delta phi corresponds to magnitude of the degree of coherence, right. So higher the degree of coherence, more temporally coherent the sources, more will be the relative change in intensity when you have a change in phase. Okay, you can say that it is more sensitive as a phase modulated sensor. Okay, so that is all fine, but let us actually dig a little more deeper and understand what it means as far as the what type of source are we quantifying now. Okay, so the question is, the point that we are making is for partially coherent light source, right, talking about temporally coherent light source, G12 is less than 1, and the question is why? How do you get G12? So what is the source characteristic that defines an partially coherent source? Okay, and to do that you need to look at you need to look specifically at what are the waves that we are interfering. In this sort of a setup, we are splitting a source wave into two. So we have this wave split into two, and the same is actually coming back and then we are looking at what we are picking up the receiver. So, what we see at the receiver is two delayed versions of the same source, right, because we just have one source here, and then we are just splitting into two and then recombining. So, when we look at this, we understand that we are looking at beating of delayed version of a particular wave. So, what does that correspond to? Well, that corresponds to the autocorrelation function of the source. Okay. So, you can write this out as an autocorrelation function. Basically, what we are saying is the autocorrelation function which may be defined so in this case that's what the mutual coherence we are looking at. So, G12 is nothing but E conjugate of T multiplied by correlated with a delayed version of that. Okay. And of course, when we talk about E of T, it is a time varying function. So, it basically corresponds to e power j omega t, or E conjugate corresponds to e power minus j omega t, whereas this one, the second term, has e power j omega t multiplied by e power j omega tau, right. So, j omega t, because we are beating this complex fields, j omega t goes out, and what we essentially are observing if we are making a measurement in the baseband is you can write this as magnitude of G12 multiplied by exponential of j 2 pi let us say nu naught is the center frequency. So, nu naught multiplied by tau, where tau is the delay between the two arms. And where is the delay coming from? The delay is coming from the fact that you are able to physically change the path length of one arm with respect to the other, right. So, essentially a Michelson interferometer is measuring the autocorrelation of any given source. Okay. Now, the key to understand is what does it mean in terms of the spectrum of the source. So, how do we associate the autocorrelation function to the spectrum of the source, and that is where we can go to what is called the Wiener-Khinchin theorem, which says that the power spectral density of a source and autocorrelation of a source are the autocorrelation function of a source are essentially Fourier transform pairs. Okay. So, let us say S of nu is the power spectral density. So, S of nu can be written in terms of g of tau as exponential of minus j 2 pi nu tau, okay, and so that is integrated over all possible values of tau, right. And similarly, once you know if you measure S of nu, you can find out g of tau as well. So, g of tau is going to be given by minus infinity to plus infinity, an integral that you do over all frequencies s of nu exponential of j 2 pi nu tau, right. So, essentially if you know the let us say the power spectral density, let us say you use a spectrum analyzer and you are able to figure out the power spectral density, and let us say the power spectral density is something that looks like this, then based on this you can actually take a Fourier transform. In this case, inverse Fourier transform will go from frequency domain back to the time domain. So, you can get g of tau, and g of tau now will look like this. Okay. So, I made it look like it's sort of Gaussian shape, but it could be any arbitrary shaped spectrum, and you can get similar a corresponding Fourier transform you can take, and you can get the other spectrum. So, the interesting part here is if you look at the spectral width, let us say the full width half maximum of your spectral width, that will have some relationship with the coherence time, the full width half maximum of this autocorrelation function. So, that is actually, oops, sorry. Is inversely proportional to delta nu. So, essentially what we are saying is if you have a larger spectral width, you have a smaller coherence time. And so, what is the implication of this? Well, the implication of this is when you go to this sort of a setup, we made it, or rather maybe it is even more apparent in this. We said we can keep moving this mirror D2 with respect to D1, and you can keep going up to whatever path length difference, that is D1 minus D2 could be whatever value, okay, could be in the order of meters, kilometers, or thousands of kilometers and so on, and you would still have this sort of beating happening. Okay. That is the kind of picture that we projected initially. But now what we are saying is, not only is your this particular interference cannot happen over such a long distance. Okay, you will essentially have this interference only over a certain distance. Okay, so it is not over infinite distance, but now it's that interference can happen or it's measurable only within this region. So, the true picture to look at when it comes to understanding the interference is something like this. So, this actually may not be the true picture, because all said and done, when delta phi equal to 0, that is actually the autocorrelation of the wave when the delay is 0. So, that one wave just correlated with another wave. So, that should actually give you maximum correlation, even if the degree of coherence is very small. So, this picture is actually a little I would say misleading. So, I would not rely on this. Rather, I would go to this other picture where I would say, okay, let us say this is my the total intensity that I am measuring, let us say okay. Well, I will just go to a different color here, so it is easier to pick this up. So, let us say this is tau, and you are looking at, or let us say you are looking at I of t, the total power, and we know that the average, if I1 equal to I2 equal to I0, that average is going to correspond to 2 times I0, and the maximum will correspond to 4 times I0. Okay. But now what we are saying is, since you are looking at a partially coherent source, you are looking at G12 less than 1, then you are not going to have interference forever. So, you would essentially have interference only over this region. Okay. And so, that actually defines the envelope of this interference that corresponds to this envelope over here, and within this you will have this changes in phase. Okay. So, well, there are actually too many lines over here. So, let me just go back and redraw this. So, we are saying that the envelope will look something like this. Okay. And the actual fringes will look something like this, right. So, those are the fringes that we expect. So, of course, if you go for quite narrow line width, when delta nu is very small, then that means tau c is very large, and then this will just sort of get flattened out. So, you will see these fringes going to minimum to maximum over larger values of tau, or in other words, we can actually represent this in terms of delta phi now, right. So, for larger changes in phase also, or larger path length differences, you can still get very good interference. On the other hand, if your source coherence is limited, you can get coherence only, or these interference fringes only with with over some limited range of delta phi. Okay. So, once again this corresponds to tau c. Now, how does tau c relate to delta nu? You can just say if your it depends on the shape actually, right. So, it's the shape of the spectrum. So, if you have a rectangular shape spectrum, right, then tau c will be 1 over delta nu. Okay. But if it is let us say a Lorentzian shape, which is the which is a commonly seen shape for the spectrum, then tau c is given by about 0.32 over delta nu. And if it is a Gaussian, so if it is a Gaussian shape spectrum, then tau c equals to 0.66 over delta nu. Or maybe yeah, right. So that is the relationship between tau c and delta nu. Okay. So this actually tells you that maybe we started with this question as to what sort of source you should use. So for long path length differences, if you want to make a measurement, let us say over 10 kilometers, okay. So that is something that we are working on right now. We are developing a sensor which can actually pick up perturbations at a distance 10 kilometers away. So the sample arm is extended to 10 kilometers. Now we are looking at a OTDR type of setup, right. So we are looking at a sample arm that is 10 kilometers away, and then some perturbation there we need to pick up, okay. So you need to support path length differences of 10 kilometers. So you need to have correspondingly high coherence source. So that is one thing we have not done so far. So let us see over here, how does this coherence time correspond to coherence distance? Well, that is simple, right. You basically say coherence length LC is just the velocity of light in free space multiplied by tau c, okay. So let us actually take that up in a separate page. So we say that the coherence length LC equal to C multiplied by tau c, okay. Now let us actually try to figure this out for different values of source spectrum. So for Fabry-Perot laser, okay, which has delta lambda in the order of 1 nanometer, okay. If for a Fabry-Perot laser, delta lambda equals to 1 nanometer, and if you say this is 1 nanometer, delta nu equal to C over lambda square delta lambda. So lambda, let us say, so this is lambda c, let us say that is the center wavelength is 1 micron, right. So this is 3 into 10 power 8 divided by a micron square. So this is 10 power minus 12 and this is 10 power minus 9, right. So that corresponds to 3 into 10 power 11 hertz. So that is basically 300 gigahertz, right. So delta nu is 300 gigahertz. So what is the corresponding coherence length? C equal to so LC equals to 3 into 10 power 8 divided by delta nu. So this is 3 into 10 power 11, right. So that corresponds to coherence length of 1 millimeter, So, yeah, that would be in the order of 1 millimeter. So, what does that mean? It means that even if your path length changes, delta D is in the order of 1 nanometer, 1 millimeter, you're going to have the interference fringes go down by a factor of half, right, because coherence length corresponds to the length path length difference where this envelope falls down to half the value, right. So the fringe contrast would have now gone down by a factor of 2, right. So on the other hand, so this is for Fabry-Perot laser, and of course we have assumed that tau c equals to 1 over delta nu for simplicity. That's, we assume that it's a rectangular spectrum. In reality, it's not a rectangular spectrum, it's more like a Lorentzian spectrum. So there's a factor of 0.32 also that comes into the picture. So it will be more like 0.32 millimeter. But we're just neglecting that for a minute. So for a LED, if you use a semiconductor LED, right, delta lambda equals to 50 nanometers. Okay, so then this would be even smaller, right? Instead of 1 millimeter, you will see that the coherence length would correspond to 1 millimeter divided by 50, which corresponds to 20 micron. Okay, so if you use a broadband source, you can actually have this interference fringes only for a very short distance, whereas if you use a narrow band source, I mean, you can go to even 1 megahertz is a DFB laser. At the 1 megahertz, you can do the scaling and you'll find that that will already corresponds to hundreds of meters, right? So if you want to have path length differences of hundreds of meters, you would go to 1 megahertz. If you want path length differences, if you want to pick up phase perturbations from distances as high as tens of kilometers, then you may need to go to kilohertz type of line width. So that's the key part in a phase modulated sensor. You know, where you want to, what sort of path length differences you want to pick up your perturbations. According to that, you need to have a corresponding source spectral width, that supports that. Okay, like I said, long path length differences, small source spectral width. Or on the other hand, if you want to have path length differences only in the order of micron, one application of that is optical coherence tomography, which we'll probably talk about in the next lecture. We will see that there you need to have very low coherence, so maybe an LED would do the job for you. Okay, so let's stop right there.